Hello, everybody. Welcome back to AP Physics with Mr. O'Hagan. We have three topics today. We're going to be doing Newton's Law of Gravitation. Nothing new. You had this last year in physics. We're going to be doing gravitation and superposition. Again, a very easy concept. It sounds intimidating, but it's easy. And then last is gravity near Earth's surface, which earlier today, you thought would have been easy, but actually it's not even close. So let's start off this by Newton's Law of Gravity, Newton's Law of Universal Gravity. Okay, so let's say you've got an object here on Earth. So there's the Earth. Ooh, my green's running out. You got an object there on Earth. And here it is. And it's got some mass. And I want to know the force of gravity trying to pull it down. Well, this should be easy. Force of gravity is, because it's near the Earth's surface, mass times g. Yay! Okay, this is not what we're talking about for Newton's Law of Universal Gravity. This is actually a special case of using Newton's second law to find out how much the Earth pulls something down. All right, so great. That's not what we're talking about. Okay, so here we go. Newton's Law of Gravitation, pre-written to save some time. So here's what this is. Let's say you have objects not near Earth's surface. So I don't know. Let's say you've got a really big, hot, burny thing. What would you call that? Oh, let's call that a sun or a star. And then way over here, you've got a little thing, kind of cold. Let's call that a planet or Pluto, except I don't think Pluto's a planet anymore. Anyway, whatever. You've got something. They are going to be attracted gravitationally because they both have mass. So there's going to be a force gravity pulling the sun to the right. And of course, I know right and left are relative things, but anyway, just go with me. And there's going to be a force on the planet pulling it to the left. And again, a gravity force, a force gravity. And Newton's third law says these are going to be the same number, just different directions. Okay. So the big mass of the sun is hardly affected at all by the force gravity due to the fact that there's a planet by it. But the planet is greatly affected by the same amount of gravity force on the planet because it's a lot smaller. But anyway, here we go. Here's how you come up with this force gravity. We had it before, just bringing it back up again. So the force gravity is equal to this thing called big G. That is the universal gravitational constant times M1 times M2. And M1 would be just the mass of the sun in this case. M2 would be mass of the planet. So it's mass of one object times mass of the other object. Divided by, and I like to put my little division just over the M's, under the M's, but of course the G's up in the numerator too. R squared. And R, of course, is the distance between the two objects squared. Since R is a position vector, that's actually like technically what it's supposed to be. Last year, I think we used a D. Maybe we used an R. I don't know. But last year, I would have explained the R by saying, hey, the planets go around at some radius, so it comes from the radius. No, R is just the position vector. That's what we use here. Okay, so anyway, I think that's about it. I got to let you know, big G, this universal gravitational constant, is equal to 6.67 times 10 to the minus 11. And the units on this, it has to end up being newtons. So it's going to be, think. I should have thought this out ahead of time. So what are my units up here? I've got kilograms squared over meters squared. And this eventually, that's this part, this eventually has to get to be newtons. And newtons are kilogram meters over seconds squared because it's a mass times an acceleration. So what do I have to do to this to make it that? I've got to divide by a kilogram. So it's going to be kilogram and it's going to be seconds squared on the top. And I got to get my meter squared on the top, one on the top. So it's meter. Wow, what weird units. Meters cubed. I'm sorry. Meters cubed on the top, kilograms divided by seconds squared. All right, those are the units. And that's just that to make the units work out, because when the universe created gravity, it did not contact Earth and say, Earth, what units are you going to be using? All right, so we picked our units, and it doesn't quite work out that mass times mass divided by distance squared is going to equal a Newton. So we have this little fudge factor to make sure that when you multiply a mass times a mass, divided by radius squared. In this context, you end up getting a certain number of newtons. Okay, so this is all just to make the thing work out. All right, I would do a sample problem of this, but it's really easy. You just plug in numbers and done. Okay, all right, next. Gravitation and superposition. When I was in high school, this word superposition, it freaked me out. It was so scary. All right, here's what it means. It's something in my eye. All right, this is actually pretty darn easy. Let's say I've got 4 masses. All right, so I got a mass here, and I'll just call this one M. I got a mass over here, and I'm going to say this is 2 kilograms. I got a mass over here, and this one's 2 kilograms. And I got a mass up here, and this one's 2 kilograms. So they're all 2 kilograms. And by the way, they're all the same distance away. I know I didn't draw it that way, but that's R, and that's R, and this is R. So they're all the same distance away. And if I want to figure out how much gravity is pulling on M, well, gravity comes from 3 spots. It comes from the force up here, the force to the right, and the force to the left. Now, since both these masses are the same amount, these 2 forces are going to be the same forces. So guess what? We don't even have to include them in the calculation. It's this idea of gravitation, superposition. It's really just, can you kind of do the vector addition ahead of time and not worry about some stuff? So if you were going to figure out the gravity on this using superposition, well, you would take the solution from this one, impose it upon the solution from this one, and they cancel each other out. You're left with just the solution of this one. Okay, another way you can do this. Let's do 5 objects, okay? And again, I'm going to make the same distance apart just because it's easy. All right, so we got the mass in the middle, mass, and we got this one up here, and this one over here, and this one over here, and this one over here. And I will make this 5, and I'll make that 7, and I'll make this one 3, and I'll make this one 3. Okay? Now, superposition says, hey, if I'm trying to figure out the force of gravity on this, I can just assume those don't even exist, right? And if I'm trying to figure out the superposition or the force of gravity on this, I can assume this one doesn't exist and say this one is instead now just 2 kilograms. All right. So this mass was really a mass of 5 and a mass of 7. I'm sorry, a mass of 5 and a mass of 2. Well, the 5 one gets canceled out by this 5 one, and I'm just left with my mass of 2. So now NOW use 2 kilograms. Okay? So that's superposition. It'll come back. I guarantee you. We'll talk about it more. But I got an itchy head today. All right, that's it. Okay, so now let's do the next one. Gravity near Earth's surface. Here's where it gets a little bit kind of crazy. If you take an object and drop it, and you want to know its acceleration. So acceleration, all right, so here we go. You drop an object and you measure its acceleration. So you drop an object and measure its acceleration. You get G. All right, this should not be any big deal. It's called the acceleration due to gravity, okay? But actually, it should really be called the free fall acceleration. We'll talk about that a little bit later. But there's a starting idea. You get this idea, you get this G, okay? Now, G, this number G is really easy to measure. You just drop something, you measure it. You know, I don't know, use a, what can you use? Anything. You take a video of it, use the video to get G. You could drop a picket fence through a photo gate, you can get G. G is super easy to measure. G is really not easy to calculate. All right. G is not easy to calculate. And guess what? You're going to have to calculate it. So you better pay attention. All right. So here's why. There are three reasons why G is not easy to calculate. All right. Here's why. All right, here's why it's not easy to calculate. First reason, all right, radius of Earth is not constant. Okay, radius of the Earth is not constant. And although this is true, this is not what I'm talking about. The Earth actually is, if it's spinning around, if you measure across the equator, it's a little bit bulged out compared to measuring from pole to pole. But that's true, and that would add into this, but that's not really what I'm going for here. I'm going for things like, hey, I want to figure out what in Livonia, are we the same distance away from the center of the Earth as you would be in Denver, Colorado, or at the top of Mount Everest? All right, got the idea? They're just different elevations, different distances above sea level, which play into how much is gravity. Because you remember that law of gravitation, where'd it go? The distance between objects, so the distance between these distances that's a center line to center line. So the difference between the center of the Earth and an object at sea level is different from the distance between an object The distance between center of the Earth and an object at sea level is different from the distance between the center of the Earth and an object up in the mountains someplace. Okay, that's what I'm talking about. So that's the first thing. Radius of the Earth is not constant. Next thing, Earth does not have a uniform density. Not have uniform density. All right, and if you remember from your science, there's different layers. There's the crust, and then you got the core, and then there's a mantle. That's not the densities I'm talking about, okay? What I'm talking about here is there are some areas of the crust which are much higher density material than others. In Livonia, we got just pretty much just random stuff in our ground. But if you go up to the UP, how about around Copper Mountain? Okay. Guess what's right under the surface there? A whole ton of metal. What's more dense, metal or just like earth and rocks? The metal is. So that can tend to throw off your gravity if you just drop something. So that's what we're talking about with that one. And by the way, I'm going to show you how to get gravity, this G. I can't deal with that. I have no idea I can't correct for that. I can correct for this one. The radius isn't constant. And I'll be able to correct for the last one. And the last one is the Earth spins. Earth spins, rotates, what spins. Spins is a good word. INS. Those are the three things. And I'm going to show you how you get G, and you got to take into account the fact the radius is not constant. In fact, the Earth spins. All right? And so let's move on. Okay? All right, so let's start with using universal gravity. And that's only going to get us so far. All right, start with universal gravity. That's supposed to say universal gravity. Oh, well. Okay, so here we go. Force gravity equals this big G, mass Earth, other mass divided by radius of the Earth squared. Okay, so that's our starting point. All right, let's use Newton's second law to get the acceleration due to gravity. All right, so force gravity will cause this mass here to have an acceleration. What acceleration? It's the acceleration due to gravity. Okay. All right, the Earth is pulling on it with a certain amount. It's going to cause it to have a little gravity. Okay, so once we have that, really, if I want to get the acceleration due to gravity, all right, let's do this. Acceleration due to gravity is the force gravity divided by the mass. That makes sense, just rearranging Newton's second law. Apply this up here. So basically, take both sides, divide it by the mass. So the acceleration due to gravity, based upon the Earth has mass and the other object has mass, is equal to is equal to big G, mass of the Earth, divided by radius of the Earth squared. Okay, so far, so good. We like this. All right, so what does this depend upon? This depends upon how far you are away from the surface of the Earth. And so that's pretty much it. Here's the kicker. All right, here's the part. This acceleration due to gravity, which I just wrote there, does not equal G, does not equal the free fall acceleration. They're slightly different. And I think it's easy to understand why they're different. All right. And up till now, we've always said they're the same thing. But here's what's going on. Imagine, if you will, we've got the Earth here. Okay, this is what we usually do. We just say, hey, here's the Earth. Here's my object. There's some forces on it. There's going to be a force gravity, and there's going to be a force normal. And we usually say force normal equals force gravity. That's what we usually say. But can that actually be true? It can't be true. And here's why. I mean, it makes perfect sense. It can't be true. The real case we have is we are on an Earth. And what's that Earth doing? It's going around in a circle. So if we take and we put onto that Earth some type of mass, well, guess what? The force gravity down and the force normal can't be equal. Force gravity must be bigger than force normal. Not by a lot, but it must be bigger to have a net force towards the center of the Earth to cause this object to go in circular motion. So that's kind of what's going on. That's why these two things can't be the same. All right. All right. So let's just kind of, I'm going to redraw this again on the next page, and then we'll take this a little bit further. Okay. So let me get my picture here. Let me do it right. Okay, so there's the Earth. Onto the Earth, we're going to put some object, and that object, of course, has mass. And the Earth has some type of angular velocity, which I will say, hey, it's going around with some omega. Yay, like that. All right, here come the two forces. We've got ourselves a force gravity, and we got ourselves a force normal. Okay? And let's assume down is a positive direction. Assume down is positive. Okay, so let's find out what the net force is here, and that net force is going to cause that mass to have a centripetal acceleration. So let's do that. So force gravity minus force normal is going to cause the mass, whatever that mass is, to have a centripetal acceleration. Yay. All right, now, each one of these parts means something, okay? So let's see if I can do, I'm going to do this. The force gravity part, this force gravity is force gravity equals big G, mass of the Earth, other mass, divided by radius of the Earth squared. So that's the force gravity. Okay, the normal force, this is where G comes in. Force normal, although the force normal is not equal to force gravity, force normal is actually equal to mg. All right? So when we said force gravity is mg, that was a lie. But we said, hey, it's a flat surface, and the normal force equals force gravity, and that's mg. That was actually the truth. All right? So the normal force is this mg part. Okay? And, of course, mass times acceleration. All right, so I'm going to take this chunk here a little bit further, and I'm going to say the force gravity equals, and it's going to have to do something what we saw back here. I'm going back to this. All right, I'm going to say the force gravity is going to equal the mass times the acceleration due to gravity. Okay, so what I've done is I've got this universal gravitation, and I'm going to say, hey, acceleration due to gravity times the mass equals this. Okay? So now I'm going to rewrite this equation, and it's going to be in terms of accelerations. All right? So I've got, and here it comes. Just bringing it down. M acceleration due to gravity minus mg causes the mass to have a centripetal acceleration. Easy peasy lemon squeezy. Okay? All right. So, and of course, we've established those two are not the same. And it's not going to be a big centripetal acceleration. These numbers are really close. I'm going to factor out the acceleration. No, the masses. All right. So, acceleration due to gravity minus g is going to equal the centripetal acceleration. And remember, the whole point is we're trying to calculate what g is. So I'm going to take this and I'm going to put it up onto the next page. And I'm going to say, make sure I got this lined up good. I'm going to say, what did I just had? I had, acceleration due to gravity minus, I had acceleration due to gravity minus, hey, I guess this one's not rated for kids anymore. All right, equals the centripetal acceleration. So here we go. That was just what was on the previous page. Now, let's solve this for g. G equals the acceleration due to gravity minus the centripetal acceleration. All right, I think I can deal with this. Oh, my page is starting to blow around. All right, so here we go. Let's do some calculations. Let's figure out what some stuff means. All right, this acceleration due to gravity, and I wish my green marker wasn't dying. The acceleration due to gravity, we've got this one. This is going to be big G, mass of the Earth divided by radius of the Earth squared. So remember, we said there were three problems with, what did I actually say? Oh, G is not easy to calculate because of three things. First thing was because of the radius of the Earth. It's not the same everywhere. Well, here we go. Wherever you're at, use that radius. Okay? So that's how we get around that problem. The density one, can't deal with that. All right? But the fact the Earth spins, we can deal with that. So centripetal acceleration, what's centripetal acceleration equal to? Centripetal acceleration is omega squared times radius. But this isn't any ordinary radius. You got to be careful. This is going to be a perpendicular radius. Perpendicular radius. Okay? So that did not show up as dark as I'd hoped. Well, anyway, I don't care. I'm moving on. Let's talk about this. If I've got an Earth and it's spinning about this axis, and I want to know what is the force, what is G at this spot right here, that spot right here. Okay, so from the center of the Earth over to here, this is what we call the radius of the Earth. That's easy. All right. And you add however far you are above sea level or whatever. Okay. Now, the radius that we need for the centripetal acceleration is all about how far this point is away from the spin axis. Because this thing, as it goes around, it's going to be going around this circle. It's not going around a circle at the equator, a big circle. It's got this little circle. So this chunk right here, this chunk right there, that's the perpendicular radius. All right, I'm probably not dark enough. That chunk's the perpendicular radius. Okay, this is the regular radius that we usually care about. That's the perpendicular radius. And there's a way with trig to get through that. If you want to know, I'll tell you. This angle, how far are you up? That's the latitude angle. That's all it is. If you know your latitude, all right, in degrees, easy. You got that. Make a right triangle here. And this is the perpendicular radius right there, perpendicular radius. So to get that, you take your radius of the Earth, multiply it by, what is that, cosine of the latitude. Because latitude is just the angle. You know, at the equator, 0 latitude, straight up top, 90 degrees of latitude. All right, so there's we go. We got this. So if you wanted to actually calculate gravity, G would equal, all right, big G, mass of the Earth, over radius of the Earth squared. minus omega squared. Omega squared. Oh, omega is, let's think about this. Omega is angle over time. So in one rotation, we go 2 pi radians in the period it takes to go around once. Period of rotation. That's 24 hours. Got to convert that to seconds. Times this r perpendicular, and r perpendicular ends up just being radius of the Earth times cosine of the latitude line. Okay? So anyway, I'll write omega squared r perpendicular, but if you want to do it again, g equals big G mass of the Earth over r Earth squared minus 2 pi period of the Earth times radius of the Earth cosine of the latitude. Cosine. That's it. That's how you come up with it. And now what have we taken into account? We've taken into account where you are compared to the center of the Earth. We've also taken into account the spin of it. The spin of it. So there's our equation. Well, I don't know which equation you want to go to. I guess maybe this is important, showing that G is the difference between the acceleration due to gravity and the centripetal acceleration. Centripetal acceleration is really small, so they're pretty darn close. All right. And if you want to take this to its logical outcome, here's how you would calculate G. All right. Acceleration due to gravity, and then minus off a portion because of the centripetal acceleration. Okay, because G is always a little bit smaller than the actual acceleration due to gravity. And let's talk about that. Why is G just a little bit smaller? I mean, I think it makes sense. Imagine, I'll do it on the next page. All right, and let's write this up here again. G is equal to acceleration due to gravity minus the centripetal acceleration. So G is going to be a little bit smaller. Think about this. Think if you had ground and you dropped an object. Oh, no. You didn't drop an object. You let it have some type of initial sideways velocity. So it had some initial velocity. And now you drop it. Drop. Or I guess shoot it sideways. If you do that, what's it do? Oh, it's projectile motion. It's a parabola. Yay, we got that. We understand that idea. Okay, now, think about on Earth. Okay, Earth isn't flat, contrary to what some people believe. Earth is a big old giant ball. So here's my big old giant ball. There's my big old giant ball. And if I got an object, and here's me, I'm just holding the object. Here's Mr. O'Hagan with my itty-bitty pinhead, and I'm holding the object. And I just let it go, it does a projectile motion because, remember, the Earth is spinning around with some type of angular velocity, and I'm on the edge of that Earth. So up here, this object has some sideways velocity, some tangential velocity. I let it go, it does projectile motion. Now I think the distance to the ground is this. Here's what I think. I think this is the distance to the ground. I measure that as the distance to the ground. But how far does this actually fall? It doesn't fall that distance. It actually has to fall more. It falls a greater distance because the Earth is spinning. Now, I drastically exaggerated what's going on, but this is the idea. It falls a greater length. All right. So the amount of time that you measure for an object falling is a little bit bigger than it should be based only on gravity because it has to fall a little bit further. All right. Since the time. Okay. So remember, so what's the equation for how far something falls? The equation for how far something falls is delta x equals 1/2 acceleration time squared plus velocity initial time. All right, so in the up-down direction, we got none of that. So it comes down to this. All right, I measure a bigger amount of time than I should get because the Earth is rotating. I keep that as the distance I think it is. It's actually a bigger distance. I keep that as it. And what happens to the acceleration? The measured acceleration has to be a little bit smaller. The free fall acceleration, this g has to be smaller because, all right, so if t is a little bit bigger, then acceleration has to be smaller. And that's what we're seeing up here. And of course, I think that's the same no matter what. All right, so that's what's really going on. That's why there's differences. That's why this is the free fall acceleration. It's not exactly the acceleration due to gravity. Back over here, here's all the good juicy stuff. All right. But anyway, that's gravitation near Earth's surface. A little bit more than you hoped for. Anyway, I hope you enjoyed today's video. Adios, everybody.